So I plan to, in this lecture, finish the calculation and then try to compare our results on the curved space with that of the flat space results. And then I do want to get to the non-trivial subspace manifold, at least to show you how the manifold is constructed and how the calculation can be done. So let us just recall what we did yesterday. So what we did yesterday was basically review localizing procedure. Anyway, you modify the path integral by something which is exact, and then which means it does not change the path integral, and then you send this number to infinity, and then the path integral localizes to the critical point of delta v. And then we have analyzed what are the critical points of this. So the critical point for vector multiplet is the set of equations given by three equations: the vanishing of the horizontal component of curvature, the vanishing of the self-2 component, plus covariant constancy of a scalar. So this will tell us that the moduli, and then we specialize it to the case of zero instant of sector, which means our moduli will be just given by the scalar field being a constant value in the algebra. And then for hyper, the critical point, the critical point is simply everybody equal to 0. And then we also saw that the second procedure after this is that you go to one of the critical points, in this case, given by these set of conditions, you compute a certain determinant, and the determinant to be computed is this one, the square of the delta. And then this is equal to, after some gauge fixing procedure, this is equal to two cases. Oh, yesterday I forgot a whole bunch of i's, but there should be an I here and there. And then so this is for the vector multiplet, and this is for hypermultiplet. And then this is the spinor derivative introduced yesterday, because the fields in the hyper remains spinors, while for the vectors we have to turn them into differential forms. So the task today is quite simple. We just compute these two this determinant for these two cases. And so then just write down, okay, in fact I can even write down the final answer. The final answer is that you just evaluate this classical action at so final answer is of this structure. You just evaluate the classical action at the critical point, which is given by a single number. Plus two determinants for hyper for vector and determinant for hyper. So that's the structure of the final answer, and then these two things will be computed today. Okay, so any questions as to what we're going to do, or general structure? So really should put my inverse here because the determinants go in the denominator.
And why do you have two equations there?
One is for vector multiplet, the other is for hypermultiplet. So the only difference is that you replace spinor Lie derivative with Lie derivative with spinor Lie derivative.
It's not a pair of equations in two different cases.
Two different cases. Okay.
So is G sigma 0 the commutator with sigma 0?
So yeah, for vector it's a adjoint action. For hyper it's whatever reputation you've chosen. Okay, so let's just do vector multiplet first. So we'll be computing superdeterminant delta squared over the following fields. We have the H field. We have this is an odd one form, and then ghost and anti-ghost. So and in fact, so the general strategy is following. Again, let me just make a remark that I always suppress the discussion of ghost to zero modes. So there really should be some zero modes hanging around that you have to take care of. But let me just not do that. So let me just say in words what's the general strategy. It is following. So you organize all benign fields into a complex such that equipped with a differential such that delta commutes. So when you put your fields into a complex like this with a differential that commutes with the operator for which you are computing the determinant, and then so the odd fields will go to the even degree guys will correspond to the even fields, and odd degree guys will correspond to the odd fields, and which means when you compute the superdeterminant, these items, the even items, will contribute upstairs, and then the odd items contribute downstairs. And then since delta commutes with, so delta is going to send a mode in this complex, in this vector space of a given eigenvalue for this operator to a mode with the same eigenvalue except now it's fermionic. So that contribution cancels. Okay, so by using this strategy, we are able to get almost all of the modes to cancel out, except those who fail to cancel out. So those modes that fail to cancel are in either the kernel of delta or the co-kernel of delta, which means
delta squared is 0?
Yes. Which means that you compute, so you have even it's the same thing as computing as determinant. H is the homology group. So the rest is on the start.
Aren't you doing S twice? You have S determinant, but also you have E divided by I. It's the same thing.
Sorry. Right, yeah, so S determinant means this determinant. Okay. So this is and then this is a finite, this is usually infinite dimensional, but this is going to be a finite dimensional if delta happen to be elliptic. So now the next task is simply to decompose these fields and put them into this shape. So let me just.
Big delta or little delta elliptic?
Sorry?
You said delta elliptic. You have a big capital delta and a little delta.
Big delta. Big delta.
It's the ellipticity kept big delta.
So, okay, let me first write down the answer, then I'll explain. Can be organized. Oh, sorry, I forgot the field, a very important field. It's, sorry about this. This is a true form, which is horizontal and anti-self tool. Otherwise, you count the number of Fermionic degrees of freedom and the bosonic degrees of freedom, they are just not equal, so there's no chance of canceling, but sorry about this.
What about sigma?
The sigma will be here. It's the moduli.
Well, one mode is the modulus, but you've got infinitely many modes. Don't they appear in this domain?
Not anymore, because so what happens was that if you remember in the toy model story, we have this kind of situation, and then in the end, the determinant to be computed. You always take the determinant and compute it on a space of coordinates, not the momenta. Okay, so yeah, if you write down what's the delta, you realize that these are the fields that appears coordinate.
What's the side? Right?
I'm so sorry about this. I'm so sorry. So it's, yeah, it should be chi here on the side. Sorry about this. Because you remember that delta A is equal to psi. So A is kind of the coordinate, psi is its momentum.
That's phi.
That's,
Oh, that's psi. Okay, sorry.
yeah.
I'm sorry.
Sorry.
Looks like a phi.
Okay. And then another guy which is entirely similar. So the decomposition goes like this. So A is a one form. So it's a one form, but it can be decomposed into vertical component, horizontal component. Horizontal plus vertical. For the vertical, you can write it as just the zero form because you have the kappa, which is the compact form. Now this one can be further decomposed according to holomorphic and anti-holomorphic. And similarly, I, it being horizontal horizontal self-dual form, can be decomposed as follows. It's got three components, and the 1,1 component is always proportional to the kappa. So you just put every field, insert them, take this decomposition, and then you can fit them all into this complex. Okay, so, and then what's the big delta I wrote here? That's actually the so-called transverse Debye operator. Roughly how it's constructed is following. You just take the derivative differential, you can project it down to the transverse plane, and then further project it to the anti-holomorphic components. The fact that it can be constructed really requires the Kähler-Einstein condition on the transverse plane, but it can be done. However, a big drawback is that this is not elliptic. So, I just said that I really want this one to be elliptic in order to control the dimension of these vector spaces. So we have to resort to some machinery more powerful. Namely, this is not an elliptic operator, but it's what's known as transversal elliptic operator. Namely, in the direction, in the momentum space in certain directions it's not elliptic, but those directions are being compensated by certain group action. But I'm not going to get into this because for the S5 case we can get away with something quite simple. But in general manifold, you just have to do this calculation by using the technique developed by Tia to compute these transversal elliptic, the index of these transversal elliptic operators, which is the case actually what we did for the YPQ space. But since this is kind of technical, I'll just go back to the S5 case where we can use some pedestrian tools to get away with it. And then just one word about what happens to the hyper. So for hyper, it's a super determinant over Q, which has plus chirality, and then a fermion field, which has minus chirality. And then if you recall, the way we chose our spin representation, they are represented actually by horizontal antiholomorphic forms, which means these two fields simply just fit into this complex without the lower one. But the calculation will be almost identical, so I will just focus on the vector mode. In fact, I just focus on one of these complex, the other one is just the same thing. Any questions? So, let's go back to S5. Let me remind you that S5 is a very special Zapata manifold, namely its orbit is regular in the sense that its orbit is always closed everywhere. And then its orbit is actually just the S1 of this U1 fiber. So what we do is the following, just use a very simple trick. It's just Fourier transform, and we call the coordinate of this theta. Fourier transform every field. According to its moment, according to its mode along the theta direction. And then, quite obviously, has eigenvalue, n. And then phi n, it depends on CP, because we have already Fourier transform, so it depends on CP2 on the base only. But it's not a function of CP2, it's a section of the ON bundle on CP2. And with this decomposition, we can actually decompose this complex termwise. So decomposing it termwise, that means each term omega 0, 0, CP2, O, and sorry, that's too small. So we just decompose that complex termwise according to their mode. Where's the eraser? And then what used to be the transverse Debye operator descends simply to the honest Debye operator on this differential complex. And now, after doing the Fourier transform full reduction along the circle direction, this operator is elliptic, and in fact, we can easily compute its index. In fact, we know even not only the index, but also the homology groups individually. So just one word about how to get these numbers. Actually, so this number here, it's equal to the so this number here is the number of degree and homogeneous polynomial of 3 variables. And so now, since all we want is the index, not actually each individual group, so the index is the following. Quite easy to see, you just take these sums and you get this single formula for any n. Okay, so now with that, we can really just finish the computation of the determinant. Any questions so far? So now determinant. Well, super determinant. It's minus I L R. Remember that R is actually just d over d theta plus sigma 0. Now for each n, we have this many modes of okay, which means this is just equal to n plus mode n gives eigenvalue for this lead derivative for n, and then there are this many modes, so you just take the product of mode n, but you still have to take take the determinant over the adjunct action of sigma 0, but that's quite simple. What you do is so that's the determinant of this thing. This is taken over. Let me remind you, this is taken over the complex omega 0, 0, omega 0, 1, and omega h 0, 2. And then for the vector multiplet, there's a similar one which you just replace holomorphic with anti-holomorphic with holomorphic. And then while for the hyper, there's just this complex alone. Okay, so which means so let me just write down the answer for the vector multiplet. So notice that here I've restored the radius, which so far have been regarded as being equal to 1, but if the radius is to appear anywhere, it's going to appear here, since the dimension of this guy is dimension of mass. And then this one has, so this contribution comes from the same computation, but with a holomorphic replacing anti-holomorphic in this complex. So this is for vector. And for hyper, remember that the delta squared for hyper, delta squared is equal to minus I. This is the spinor derivative. But recall that since we chose the spin representation as using differential form, so it's not surprising that the spinor derivative is almost the same as the usual derivative. In fact, it is equal to something. Equal to this with a simple shift. I don't want to go into the discussion of this number. This number turns out to be quite important. We'll see this in a minute. So for hyper, the superdeterminant is given by the following expression. So the mu is the weight of the representation that you've chosen for your hyper. And then why did I say that this shift is important? Because in a hyper you always have one field transforming in the representation R, the other field transforming in the representation R bar, which means it's totally symmetric when you exchange R and R bar. While exchanging R and R bar is the same thing as just replacing mu with minus mu, meaning you just put a minus on here. And then because thanks to this shift, actually up to an irrelevant constant factor, this is symmetric with respect to this change. I mean, so it's an even function of this argument because of this shift. So, which means this one, even though it doesn't look like it's a symmetric function, is implicitly symmetric with respect to the exchanging of R and R bar. Okay, so
you don't want to put mass on it?
yes, thank you. I almost forgot. Okay, now I do want to consider massive hyper. So to put a mass, we will just use the following trick. Namely, I will just couple the hyper to an auxiliary vector multiplet. And then I will turn off all the fields in the vector multiplet except giving an expectation value to its scalar field, which we call sigma here. And then the expectation value of this sigma will be called n, the mass, which means if mass is to appear, it's going to appear here. Because that's just given by a simple shift of sigma by an expectation value of the auxiliary vector multiplet. Okay, so that's our answer basically for the.
Don't you want to put imaginary I somewhere to compare electron as a flat case?
Right. Okay. Yeah. Yeah. Maybe. Yeah. Sorry. Maybe I made. Yeah. Okay. Sorry. Sorry about this. Actually, eyes everywhere. Sorry. It's a typo. Yeah. Because what happens was that sigma, when you do the path integral, it has to be weight rotated. So actually, so that's why this I will show up. I'm sorry about this. I just totally forgot to explain. Right, okay, so let's give these two things a name. And then we can start. And then our final answer after 3 days of travail is this. Let me call it. So, how should I say the final answer? Okay. So this part is the classical part of the action evaluated at the critical point times. So that's the final answer.
I think you have to write the carton, and you were not very careful with Vandermonde and stuff like that.
Yeah, okay. So, thank you. So what happens was that this integral is over the algebra, but the integrand is manifestly eigenvariant, so I can push the integral into not the algebra, but the Kaplan. And this way I'll get an extra determinant factor, but as I mentioned in the second lecture, this determinant factor is going to cancel from some contribution coming from the goes to zero modes, which I suppress. So anyway, so in the end, the upshot is that that's the final answer. Integration is not over Kaplan. So basically, this is the end of the calculation. Next, what we're going to do is we'll take the large radius limit and compare to the flat space. So any questions regarding answer procedures?
What happens if the hypers are in the adjoint representation?
Well, you just replace mu with
I know, but does it cancel what you had for the vector model?
No. The cancellation is not complete. So we'll see in a minute when we. So any other questions? So the comparison to flat spaces is you take the large radius limit, and then you can see quite clearly that taking the large radius limit amounts to considering what's the asymptotic expansion of this huge function. Okay, so let me just give you the asymptotic behavior of these functions. Let me just say that these functions can be written in terms of double log and triple log, so you can look up their asymptotic behavior from Wikipedia, or in fact it's much easier to do it yourself. Encroaching to this space. So this is relevant for the vector multiplet. You see that depending on the sign of the imaginary part of X, you get different asymptotic behavior. And then for that which is relevant for the hyper, the vacuum hyper, if the hyper is in the adjoint, then you see that the leading components of the leading behavior, the x cubed behavior will cancel out, but the cancellation for the subleading, well, if they don't cancel for the subleading part. So you just get, you generate an effective potential which is linear. Okay, so now I'll erase this part.
The explanation to not put the 16 superchargers as zero as a sphere because I've created some symmetries.
Well, let me just okay, so let me just write down the effective action. That's just 8 volume S5 G mu squared R squared. So that's the same thing as before. In the large radius limit, so I'm only keeping the R to the, so this is the order R to the cube. Right. Now, oh, sorry. This should be not this, but. Okay, so the leading cube behavior is always proportional to the volume of the space, and you might object that okay, these factors pi and mass just come out of the calculation. How do I know that this necessarily is the volume of the space? The reason we know this is because when we did some other calculation for white cube space, this factor will come out a complicated function of p and q plus the squashing parameter, but they coincide with the squashed volume of white cube space. So I think there's no doubt that these will be proportional to the volume. And then I might as well just factor out the common volume and call it effective potential. And then another objection you might raise is that, okay, this is already suppressed by this radius squared. So when it goes to 0, if we take radius to infinity, so what happens is that actually the comparison with the flat space computation is very indirect because in the sense that here the quantum correction generates a potential which is of sigma cubed. But this term is never going to occur in the flat space. In the flat space, what we know is that quantum correction will generate a pre-potential of this type, but this one will never lead to a sigma cubed potential in flat space. So how do we really compare with the flat space result? It'll be the following. Let me just sketch what we how we do that. So in flat space, suppose the quantum correction generates a potential, pre-potential of this type, C by 6 A cubed. And that is going to lead to the following terms. In the action, the Chern-Simons pi term plus so if you work out what's the contribution from this pre-potential, that's going to be the Chern-Simons plus the field-dependent Yang-Mills counting term plus the field-dependent multiplied by the kinetic energy for the scalar. So this is in the flat space. But these terms is superconformal. So we have a well-defined procedure of putting this part of the action onto the sphere. And then the procedure is very simple. The only modification is the following. Let me try to explain it. It's the first factor. The first factor is there so R is the Ricci scalar of S1.
Could you have meant sigma cubed instead of sigma squared?
There's a sigma outside. So the total thing is sigma cubed. And then R is a Ricci scalar. And then the function, the purpose of this term is to make sure that this combination, the combination of this guy and this guy is conformal invariant. And for this, I can't explain. It's basically what happens is that the auxiliary field, which would have zero expectation value in flat space, obtains a non-zero expectation value in a curved space. And then you see that the expectation value is suppressed by the radius. So altogether, it's just. So what we're going to do next is the following. Just do, in fact I will not do it, I just sketch what you do. What you do is that go to flat space, do a one-loop calculation. For example, you can do it in the background field method. Figure out what's the how much is figure out the coefficient of this C. So how much is being generated by quantum correction. And then, knowing this coefficient C, you can figure out if you want to put this term onto a curved space, what would be the sigma cube potential that's being generated. And then you compare this coefficient with that. And well, it works, that's all I have to say. So you get perfect match, and so because I really don't want to explain how to do one-loop calculation, it's fairly elementary.
Sorry, can you said this comes from the auxiliary field. This is which auxiliary field? This is the one that you gave the map. You used to give it a mass, or no, different auxiliary?
No, it's the auxiliary field in the vector multiplet. The one, well, I never wrote it, but it's the field that would have zero expectation value in flat space, but it does get an non-trivial expectation value. So I can't explain this in technical detail. But anyway, so the model is really to compute this term first, and then relate somehow the coefficient of C with the coefficient of sigma cube potential, and then compare it with what we got by doing the direct localization computation, and then the results match.
So can we describe it as follows? Integrating out of a massive vector or hypermultiplet gives an induced A cube term of the whole branch. Is that what you're doing?
Yeah. So yeah, you can use the background field method, and yeah.
So that's a check of your big calculation. Because that would be an explicit one-loop calculation you can do that would give a check on this.
Yes. So in fact, that's all I want to say about the stuff. Next will be about the YPQ space, at least to show you how to construct this space. So any questions before I erase everything? first of all, let me just give you some other regular Einstein manifolds. There aren't many, so we have already seen this guy, the 5 sphere. Then the rest is actually the following total space of the following bundle. So this notation is that it's a line bundle over the product, which has degree 1 here and 1 there. So this is commonly called Q11 space. And then there's this so P and pencil. So K is the canonical bundle of this space. So these are all the 5-dimensional regular Einstein. So the classification really just follows from the classification of Kähler-Einstein 4-dimensional Kähler-Einstein manifolds. Now, moving on to the irregular case. I'll just give you the construction of what I could do. So start from C4 with standard Kähler structure. So since we will need this formula and I have time, I'll just write it down. So let me call the coordinates C1 to C4. And then I'll call eta I. And then the Kähler structure, the Kähler form, omega is the standard one, just sum over all. And then let me also define some U1s. So for example, E1 is just the rotation of phase of Z1. Let's consider the following U1. Let me call it U1 sub T. It acts with following charge. Whoops. So it acts on the 4 Z's with the following charge vector, where P and Q must satisfy the following condition. Okay, so what we do next is that consider the Kähler reduction of this U1, which is just the same thing as this one. Let mu sub T be the moment map of it's equal to this. So the 0 level set of now, well, because C4 is Kähler, so after this reduction, let me call this thing C. C is also a Kähler manifold, and let's look at the shape of the moment map. Obviously, the 0 set of this moment map is invariant to the simultaneous scaling of all four coordinates. So C has a color structure. And not only that, notice that the sum of the 4 charges is equal to 0. And needless to say, C4 is Calabi-Yau. So the cone is also Calabi-Yau. Now, we know that the Calabi-Yau condition of the cone, if you work out what's its Ricci repeat tensor, it implies that the base of the cone is actually Sasaki is an Einstein manifold, and then the fact, well, it's actually Sasaki Einstein manifold. So that's going to be our shear space. So to see this space more explicitly, we can do the following. Oh, I just wrote the stuff I need. So first, let me just write down what's the read and stuff. So read vector is equal to linear combination of the EIs. Let me recall that the EIs before I erased them used to be the EIs are the rotation of the i's z coordinate. So there's going to be some positivity condition for these numbers Ri. I'll come to this later. And then the contact form kappa is the standard one, namely. Okay, let me write it again. Z. So it's the sum of all these guys. And then let's just look at so we would like to have this on the base. So on the base of the cone, we would like to have so let's just look at what is this thing. It's actually equal to well, it's easy to write. We'll just plug this one into here. We'll realize that it's just the sum of a bunch of norm squared of z's with the weight given by Ri. I want this to be 1. So, which means I might as well, I want this one to be true on the base, which means I might as well just define the base to be given by this equation, which means, let me call this, let me just call this the right-hand side mu sub R. It's sort of the moment map for R, kind of. So this is a valid base if its intersection with this cone is actually a compact manifold. So that's going to give us some conditions on what the range of these numbers are. And then let me not go there. So if you want, I can give you the precise description later. So anyway, so that's the read and the contact one form. Now to get a handle on this space, let's just make a particular choice of this thing. Let me choose to be. Notice that it differs from, recall, keep erasing stuff I need. So this is my choice for the read, and then this was the U1T with which we did the reduction. So the intersection of this zero level set with the cone is just the intersection of the two zero level sets. And then it's easy to see that this is going to be equal to, is given by the following expression. Because the only thing that differs between these two vectors is the sign that's switched. So okay, and so this is clearly just, this is an S3, this is an S3, which means that the YPQ space could be also envisioned as being S3 cross S3 divided by, remember that we always have to divide by the group function by a common U1. Now, this U1 actually acts freely on both S3 because basically the coordinates Z1, Z2 cannot be zero simultaneously being bounded by this condition, and neither can Z3 and Z4 vanish simultaneously. And then by the co-prime condition for P and Q, there is no discrete stability group either, so it's a free action. So this quotient is actually an honest quotient. So no static business needed. Anyway, so this is the YPQ space. So any questions about the construction? How much time does it have?
7 minutes.
Okay, so let's keep this one short. Let's see next. Okay, so let me just mention that we have a Cattaneo manifold, we have a reed. So we see that there's a certain degree of freedom when we choose our reed. And it's not every reed choice of reed vector will admit a Sasaki-Einstein metric. In fact, what was shown by Martelli, Sparks, and Yar was that what you need to do is the following. You can first deform the reed within what's so-called the moment to tone, and then there's a unique choice of the reed which would admit a Einstein metric, and then after that you can fix this reed and then deform. So you fix this reed, and then there's still the metric on the transverse space. And then you can still deform this metric for the transverse space, and then find a Taylor Einstein metric for this one, which is equivalent to the whole manifold being Sasaki-Einstein. And the good thing is that these two steps can be done independently of each other. So you can fix the reed first, and then do the second part. And the second part is really hard. But the good thing is that for our calculation, we actually, all we need is the reed. We don't really need what's the metric, because once you pass on to doing index computation, it doesn't care about what's the metric. And okay, so let me just write down. So this is the case if you want to do the index calculation, then for the YPQ space, what happens is that the reed does not have closed orbits everywhere. Usually it's just get 4 closed orbits for generic cases, which means the trick we use when we're doing Fourier transform doesn't work. We can't do that. So you just have to grit your teeth and do the index for the transversal elliptic operators, and then it can be done. It takes some time. And so let me just write down what will be the determinant. And write this down for hybrid, it's easier. Again, the trick is to remember that you have the space can be envisioned as S3 cross S3 divided by U1. So roughly speaking, what you do is you do index here, impose that they are invariant under, you pick out only the modes which are invariant under the common U1. So in fact, the answer reflects this construction. The answer is simple, that's it. So let me explain the notation. So AI, they are integers. And then lambda is a lattice, which the function of this lattice is exactly to constrain it onto those flows which are invariant under this U1. So its description is the following. So it's got two parts, and then this equation, this constraint for the lattice is saying that none of the modes is charged under this U1. So you can do this sum using this lattice, and then you can basically do everything you. Let me just make one final remark. This is some kind of generalization of the triple sign function, while the case for the S5, or the squash S5, what you got is actually the triple sign function. This is some kind of generalization which we are investigating now. So that's the end of my lecture. Thank you.
Question for John.
I have a question. If you push out by your foliation, the refoliation, what information do you have on the quotient?
Well, the quotient is that space because the orbit does not close. We have no idea to why the orbit.
Do you have any, I don't know if you know Alan Kahn's non-commutative geometry, the basic idea is to look at quotient spaces like that and get some kinds of invariants which are not necessarily invariants.
I cannot say anything. I have no idea about this construction.
It would be very interesting to
Any further questions? If not, let's say.